In this video, I will be discussing zeros, poles, and their relation to the time response of a system. A control system performance is measured by the transient response and steady-state response to see if the system yields its desired behavior. The output of a control system is the sum of the forced response and the natural response. Similar to solving homogeneous differential equations, the forced response is called the steady-state response or particular solution, and the natural response is called the homogeneous solution. In the equation below, y of t equals 2 plus 4e to the minus 8t will be the solution to a homogeneous differential equation. The 2 in the equation will represent the forced response, and 4e to the minus 8t will represent the natural response. We can evaluate the system's output response through the use of poles and zeros to observe their relationship to the time response of a system. The poles of a transfer function are defined as the values of the Laplace transform variable s that cause the transfer function to become infinite, or any roots of the denominator of the transfer function that are common to the roots of the numerator. The zeros of a transfer function are defined as the values of the Laplace transform variable s that cause the transfer functions to become zero, or any roots of the numerator of the transfer function that are common to the roots of the denominator. For the system g of s, we can observe that the system g of s is 0 at s equals minus 5, and g of s is equal to infinity at s equals minus 9. Thus, g of s has a 0 at s equals minus 5 and a pole at s equals minus 9. In this example, if an input r of s is applied to the system g of s, this would produce an output time response in the form of a forced response plus a natural response. The input rs to the system is a step function whose transfer function is 1 over s, having a pole at s equals 0. If we want to determine the output transform c of s of this system, we utilize partial fractions expansion, where we use the 0 and pole values to generate the amplitude for both the forced and natural response. Taking the inverse Laplace transform of c of s produces the output time response c of t. We can also observe that applying a step input or a pole at 0 generates the forced response. We can also observe that a pole of the transfer function generates the natural response. So the pole at s equals minus 9 generates an exponential response e to the minus 9t in the time domain, which means the further negative the pole is on the real axis, the faster the exponential response will decay to 0. Let's look at implementing this example in MATLAB. First, we create the transfer functions for the system g of s. Secondly, we create the transfer function for r of s, the input to the system, and afterwards we create a series or cascaded connection between the input and the system transfer function. Following that, we can plot the zero-pole map of the output transform c of s and the step response g of s. The pole zero map indicates the system pole at minus 9, the system 0 at minus 5, and the input pole at 0. We know that the output time response c of t is equal to the forced response plus the natural response. The forced response is 5 over 9, which is 0.55, and the natural response is 4 over 9 e to the minus 9t. Looking at the step response, we see that the amplitude of the output time response approaches 0.55 as the time approaches 1 second. If we choose a point on the curve, for example 0.3 seconds, we see that the amplitude is 0.585, which is the value of the forced response plus the value of the natural response at this particular time. In conclusion, we discussed zeros, poles, and their relations to a system's output response. MATLAB examples were also demonstrated to show this relation. If you have enjoyed this video, please like, comment, share, and subscribe, and I'll see you in the next video.